Types of risk-based inspection, RBI, assessment according to API Recommended Practice 580-581, Overview of Key RBI Methods for Industrial Safety. Introduction to Risk-Based Inspection, RBI, RBI Analysis in General, Scope and Objectives of RBI Assessment, RBI Analysis Methods Overview, Factors Influencing RBI Method Selection, Continuum of RBI Methods, Qualitative RBI Method, Semi-Quantitative RBI Method, Quantitative RBI Method, Expected Outcomes of the RBI Process, Inspection Planning Outputs, Conclusion and Key Takeaways. Risk-based inspection, RBI, is a structured and systematic methodology used to prioritize inspection activities based on the risk posed by equipment failure. As defined in API Recommended Practice 580 and 581, RBI integrates principles of risk management, mechanical integrity, and inspection planning to improve safety, reliability, and cost-effectiveness in operating facilities. Risk, within the RBI context, is typically expressed as the combination of the probability of failure, POF, and the consequence of failure, COF. By evaluating both aspects, RBI allows organizations to focus inspection and maintenance resources where they provide the greatest reduction in risk. The RBI framework supports informed decision-making by identifying critical equipment, understanding degradation mechanisms, and aligning inspection strategies with business and safety objectives. Rather than applying uniform inspection intervals to all assets, RBI recognizes that different equipment items have varying levels of risk depending on factors such as operating conditions, materials of construction, corrosion mechanisms, and process hazards. This risk-based philosophy is especially important in complex process industries such as oil and gas, petrochemical, and refining operations. API RP 580 provides the overarching principles and requirements for implementing an RBI program, while API RP 581 offers detailed quantitative methodologies for calculating risk. Together, these documents form the technical foundation for modern RBI practices. An effective RBI program enhances plant safety, reduces the likelihood of unplanned outages, optimizes inspection costs, and demonstrates compliance with regulatory and corporate integrity requirements. This introductory slide establishes the conceptual basis for understanding the various types of RBI assessment methods discussed in subsequent sections. RBI analysis in general refers to the overall process of identifying, evaluating, and managing risks associated with pressure equipment and piping systems. According to API RP 580, RBI analysis begins with defining the scope of the assessment, including the facilities, systems, and equipment to be evaluated. The analysis then identifies credible damage mechanisms such as corrosion, erosion, fatigue, cracking, or metallurgical degradation that could lead to loss of containment. A key element of RBI analysis is the evaluation of the probability of failure, POF, which considers factors such as material susceptibility, operating conditions, inspection effectiveness, and historical degradation rates. In parallel, the consequence of failure, COF, is assessed by examining potential impacts on personnel safety, environmental release, asset damage, and business interruption. These two components are combined to determine the overall risk level for each equipment item. The general RBI analysis process is iterative and data-driven. As new inspection results, operating data, or failure information become available, the risk assessment can be updated to reflect current conditions. This ensures that inspection plans remain relevant and technically justified. Importantly, RBI analysis is not limited to inspection planning alone, it also supports decisions related to mitigation measures, design changes, operational adjustments, and risk acceptance criteria. By applying a consistent and documented approach, RBI analysis enhances transparency, traceability, and engineering rigor in asset integrity management programs. The scope and objectives of an RBI assessment are critical to ensuring that the analysis delivers meaningful and actionable results. As outlined in API RP 580, the scope typically defines the physical boundaries of the assessment, such as specific process units, systems, circuits, or individual equipment items. It also specifies the type of equipment covered, including pressure vessels, piping, heat exchangers, tanks, and associated components, the primary objective of an RBI assessment is to identify and prioritize risks so that inspection and maintenance activities can be focused on high-risk equipment. This prioritization enables more effective allocation of resources, reducing unnecessary inspections on low-risk items while increasing attention on equipment with higher potential consequences or likelihood of failure. Additional objectives often include extending safe operating intervals, supporting regulatory compliance, and improving overall plant reliability. Another important objective is to enhance understanding of damage mechanisms and risk drivers. By systematically evaluating degradation processes and their impacts, RBI helps engineering and inspection teams develop targeted inspection plans and mitigation strategies. The scope and objectives should be clearly documented and agreed upon by stakeholders, including operations, inspection, maintenance, and management. This alignment ensures that the RBI assessment supports both safety and business goals while remaining consistent with APIA recommended practices. Selecting the appropriate RBI analysis method is a critical engineering decision influenced by several factors. One of the primary considerations is the objective of the assessment. For example, high-level prioritization may only require a qualitative or semi-quantitative approach, while detailed inspection interval optimization may necessitate quantitative analysis. Data availability and quality also play a major role, as quantitative methods require reliable inspection histories, corrosion rates, and process data. The complexity of the facility and the potential consequences of failure must also be considered. Facilities handling hazardous fluids or operating at high pressures and temperatures often justify more rigorous methods due to higher risk exposure. Additionally, organizational resources such as technical expertise, software tools, time, and budget can influence method selection. API RP 580 emphasizes that method selection should be technically justified and aligned with risk management objectives. In some cases, a phased approach is adopted, starting with qualitative screening and progressing to more quantitative methods for critical equipment. This flexibility allows organizations to balance practicality with engineering rigor while maintaining compliance with recommended practices. The concept of a continuum of RBI methods highlights that qualitative, semi-quantitative, and quantitative approaches are not discrete or isolated options, but rather part of a progressive spectrum of analytical rigor. At one end of the continuum, qualitative methods provide broad risk categorization based on expert judgment and experience. At the other end, quantitative methods deliver precise numerical risk estimates using probabilistic models. Semi-quantitative methods occupy the middle of this continuum by combining structured scoring with limited numerical inputs. As data quality and availability improve, organizations can move along the continuum toward more quantitative assessments. API RP 580 supports this flexible approach, recognizing that different equipment, systems, or facilities may warrant different levels of analysis. The continuum concept also enables continuous improvement of RBI programs. Initial assessments may be conservative and qualitative, with subsequent iterations incorporating better data and more advanced methods. This ensures that risk evaluations evolve alongside the asset lifecycle and operational knowledge, ultimately leading to more effective inspection and integrity management decisions. The qualitative RBI method is the simplest form of risk assessment and relies heavily on expert judgment, experience, and descriptive criteria. In this approach, both probability of failure and consequence of failure are categorized using qualitative scales such as low, medium, and high. Risk is then determined by combining these categories using a risk matrix. Qualitative methods require minimal data and are relatively easy to implement, making them suitable for early-stage assessments, smaller facilities, or situations with limited information. They are particularly useful for screening purposes, helping to identify equipment that may require more detailed evaluation. However, the reliance on subjective judgment can introduce variability and uncertainty in the results. API RP 580 acknowledges the value of qualitative RBI while emphasizing the importance of using knowledgeable and experienced personnel. Proper documentation, consistent criteria, and multidisciplinary team involvement are essential to improve reliability and credibility. While qualitative methods may not provide precise risk values, they play a valuable role in establishing a risk-based mindset and supporting high-level decision-making. Semi-quantitative RBI methods bridge the gap between qualitative judgment and fully quantitative analysis. These methods use numerical scoring systems to represent probability of failure and consequence of failure, typically based on predefined criteria and weighting factors. The resulting scores are combined to produce a relative risk ranking. This approach offers greater consistency and transparency than purely qualitative methods while requiring less data and computational effort than quantitative models. Semi-quantitative RBI is widely used in industry due to its practicality and ability to support prioritization and inspection planning. It allows organizations to compare risks across a large population of equipment and focus resources on higher-risk items. According to API RP 580, semi-quantitative methods should be carefully designed to ensure that scoring systems reflect real risk drivers and are calibrated appropriately. Regular review and validation against actual inspection and failure data help maintain confidence in the results. Semi-quantitative RBI provides a balanced approach that combines engineering judgment with structured analysis. Quantitative RBI methods represent the highest level of analytical rigor and are detailed extensively in API RP 581. These methods use mathematical and probabilistic models to calculate explicit values for probability of failure and consequence of failure. POF is often expressed as a failure frequency, while COF may be quantified in terms of financial loss, environmental impact, or safety consequences. Quantitative RBI requires high-quality data, including detailed inspection histories, corrosion rates, material properties, and operating conditions. Advanced software tools are commonly used to perform calculations and manage large datasets. The results provide a robust technical basis for inspection interval optimization, risk acceptance decisions, and cost-benefit analysis of mitigation measures. While quantitative methods offer greater accuracy and defensibility, they also require significant expertise and resources. API RP 580 emphasizes that quantitative RBI should be applied where the benefits justify the effort, particularly for high-risk or high-consequence equipment. When properly implemented, quantitative RBI supports optimized, defensible, and auditable integrity management decisions. The expected outcomes of an RBI process extend beyond simple inspection scheduling. One of the primary deliverables is a clear risk ranking of equipment, enabling organizations to understand where the greatest risks reside. This ranking supports informed decision-making related to inspection frequency, methods, and resource allocation. Another key outcome is the identification of dominant damage mechanisms and risk drivers. This insight allows engineering teams to develop targeted mitigation strategies, such as material upgrades, process changes, or improved inspection techniques. RBI also provides a documented and auditable basis for inspection planning, supporting regulatory compliance and internal governance requirements. Ultimately, the RBI process contributes to improved safety, reliability, and cost efficiency. By focusing efforts on risk reduction rather than routine compliance, organizations can achieve better integrity outcomes while optimizing operational expenditure. These benefits align directly with the intent and guidance of API recommended practices. Inspection planning is one of the most tangible outputs of an RBI assessment. Based on calculated or ranked risks, inspection plans define appropriate inspection methods, such as visual inspection, ultrasonic testing, radiography, or advanced non-destructive examination techniques. The plan also specifies inspection intervals, coverage extent, and inspection locations. API RP 580 emphasizes that inspection plans should be risk-informed and performance-based. Higher-risk equipment typically requires more frequent and more effective inspections, while lower-risk items may justify extended intervals. RBI outputs may also include recommendations for monitoring, maintenance, or risk mitigation actions. By aligning inspection activities with risk, organizations can reduce unnecessary inspections, focus on critical degradation mechanisms, and improve the overall effectiveness of their inspection programs. This structured output supports long-term asset integrity and operational excellence. In conclusion, Risk-based inspection as defined by API RP 580 and 581 provides a comprehensive and flexible framework for managing equipment integrity. The availability of qualitative, semi-quantitative, and quantitative assessment methods allows organizations to tailor their approach based on risk, data, and objectives. Understanding the continuum of RBI methods and the factors influencing method selection is essential for effective implementation. Each method has its role, from initial screening to detailed risk optimization. The ultimate goal of RBI is not merely to inspect, but to reduce risk in a systematic, defensible, and cost-effective manner. By applying RBI principles consistently, engineering organizations can enhance safety, improve reliability, and support sustainable asset management. These outcomes reflect the core intent of API recommended practices and represent best practice in modern mechanical integrity and inspection engineering.